All right, so we're back, and I've got our next example written up here, and we've seen that the substitution method works out really well if it's not challenging to get a variable by itself. You could technically use it for this next example, 4x minus 5y equals negative 3, 2x minus 7y equals negative 6. The trick is, it's not really all that easy to get any of these variables by themselves, and no matter what, if you do it, you're going to have fractions left hovering around. And while I'm okay dealing with fractions, most students aren't, and I've got to be honest, even with my comfort level with them, it's going to be kind of a pain to keep pushing them around in here. So if we could avoid using fractions in this scenario, it might be nice. And that's where this other method that we're going to talk about comes up, what we call the elimination method for solving systems of equations. All right, so the idea here is we want to come up with some clever way to combine these equations so that we eliminate one of the variables, thus elimination. So looking at this, it's not, again, immediately clear. When I'm talking about finding ways to combine them, I'm actually talking about straight up like adding or subtracting or something like that equations here. And it doesn't immediately jump out in this instance how that would work. But here's the idea. So what I can do, so long as, remember, I do something to both sides of the equation, I'm not changing any of its solution values, right? That's that algebraic equivalence from the first section. So what if I took this second equation here and just multiplied everything in it by negative 2? Again, this is not officially correct. I should have negative 2 over here and a negative 2 on the right, but that gets kind of tedious to write down. So I just multiply everything in that second equation by negative 2. So if I do that, I haven't touched the first one. I'm just going to go ahead and write it back up over top of, where I'm going to put the new guy. So now I basically double everything and then change its sign from positive to negative or vice versa. So that's going to be negative 4x out of the first term. Negative 7 times 2 gives me positive 14y. Again, I got to do whatever I do to the left, I got to do to the right side as well. Negative 6 times negative 2 gives me a positive 12. Now, here's where the elimination part of this comes in. Now, what I'm going to do is I'm just going to add these things up. I find it useful just to do the old addition bar, when you first learned to write out addition way back in the midst of time. Because now if I add everything up, I'm going to combine like terms. 4x minus 4x, poof, they're gone. They vanish in a puff of logic. So now I'm going to be down to just the y variable, which makes this way easier to solve. Negative 5y plus 14y is going to give me 9y. Over here I add the right-hand sides up as well, so we have negative 3 plus 12. That gives me a positive 9. So now, it's not too tough to get y by itself here, right? So 9 divided by 9 is 1. So we've got that. We've got our y. But like before, we need to get both x and y values. We've only got the 1 at this point. This is where this is kind of a downside over the substitution method. We don't just automatically have a super easy, x in terms of y equation floating around. But we can still take this y value and plug it back in to one of the equations. We could technically pick either one. I'm just going to grab that first one because it's the one I pointed at. So we have 4x minus 5. I feed in that y value of 1 that we just got from right here. Equals negative 3. And if I smash around the arithmetic to get x by itself, I'm going to have negative 3. To get rid of the minus 5, I add 5. Then I've got to divide that whole thing by this coefficient of 4 that's hovering around in front of the x. So negative 3 plus 5 is positive 2. 2 divided by 4 would be 1/2. So my overall solution again, on some level, writing x equals 1/2, y equals 1 is fine, but I know, it's kind of useful to have it as an ordered pair, but you could also write x equals 1, x equals 1/2, y equals 1, as if you were just working this out on paper. It's important, though, to be able to remember to convert it to an xy ordered pair. So that's one example down. And so, like I said, in this instance, the elimination method, I think, works better than substitution because it wasn't too challenging to, come up with a way to annihilate or knock out one of the variables and leave us just dealing with one at a time, which is, kind of our comfort zone based on the rest of the chapter. All right, so the next example, it's not quite as straightforward in terms of what we're going to need to do as far as elimination goes. But elimination, I think, is still a better road than trying to figure out how to rearrange for a substitution. So we have 5 halves x minus 7 halves y equals -1. That's a top equation. Bottom equation says 16x plus 6y equals 22. Okay, so I'm going to take for granted you've got that stuff now. If not, you can rewind and pause, right? Now, in this instance, we don't quite have that same elegant, lining up of values like we had before. There's no, offhand, yeah, technically we could figure out something to multiply, this by, but I think it's generally going to be easier to do this in stages. So we see fractions, and the fractions are scary, right? So first order of business, let's multiply everything in this equation by 2. That would get rid of the fractions. All right, I'm going to go ahead and just rewrite this for ease of reference. So now I've got -2, I have a 7, and I've got a 5 right there. Now they still don't match up, but here's what we can do. We can basically come up with things to multiply both equations by to knock out either of the two variables. I'm going to stick with killing off x because it's living up front. So what I can do is basically sort of do like a common multiple thing. So I multiply the top equation by 16. I'm waiting for the camera. It's getting a little blurry, trying to let it focus. But then I can multiply the second equation by the coefficient of x that's up in the first one. So we have that. I'm going to pause for a second. Oh, there we go. Nope, I got ready to hit pause. The camera wanted to make a fool of me. So now, like before, we can kind of work through the multiplications here. And generally speaking, I like to make these so they're opposites. You could technically do like a thing where you remember to subtract one equation from another, but I think adding makes it a little easier to parse. So we have 80x minus, when I work out 7 times 16, I got 112y. And then I've got -32 on the left-hand side. Or sorry, the right-hand side. I said that wrong. That's the right. I do remember my left from my right. So when I distribute the 5 across the second equation, I'm going to have -80x minus 30y. And then 22 times -5 would give me -110. All right. So from here, we can combine these guys once again. The x's just kind of go boom, they're gone. I combine those guys together, that gives me -142y. Over here, I get -142 again. So y equals 1 in this instance, and I'm going to leave it to you as a check that if you plug y equals 1 back into either of these two equations, you're also going to end up getting that x is equal to 1. And you can verify from looking at the original equations or with the modifications I put to them that it does end up satisfying both of those equations at once. So done and done on this guy. So we've seen substitution, we've seen elimination. All right, I've got one last example I want to take a look at here, and it ends up sort of looking like something that we've already done. So this last example is sort of a callback to from the very first section to Joe and his investment strategy, except now we've got somebody trying to sell concert tickets. So according to the example, they want to make $84,000 by selling 16,000 tickets. And we know that the upper deck tickets only sell for $40, whereas the ones down below sell for $60. So that's sort of the machinery we're working with. So you could technically set this up like we did with Joe, but instead, let's set this up as a system. So I need to assign a pair of variables this time. I'm just going to say X is the number of tickets we sell from the upper deck, Y the number of tickets, from the lower deck that are, a little closer. So now we can write two equations that describe what's going on here. So our concert promoter wants to sell 16,000 tickets. So if we add up X and Y, that should give us 16,000, right? Right. Now, the other thing we've got in play is how much money we're wanting to make. We want to make $84,000, and we know that when we do that, each upper level ticket we sell, we get $40 of income. Each lower level ticket, we get $60 of income. And so now we have our system of equations set up. And at this stage, technically, you can choose either method to solve this thing. So I labeled this elimination. I actually think, once again, substitution is actually not too tough to do. So, because we can get either variable by itself in that first equation just with a straightforward subtraction. So by elimination, we don't quite need you for this. So X is 16,000 minus Y. We plug that down in here. So we have 40 times 16,000 minus Y plus 60Y equals 84,000. All right. Now, we distribute the 40. We get 64. Sorry. Double checking to make sure I'm doing this right. So I actually did this slightly differently. So it should be 64, it should be, I'm missing a 0 in my initial thing. That should be 840,000. I was trying to figure out why the numbers weren't lining up like I thought. So sorry about that. That should be 840,000. My bad. So, because when I worked this out, I was like, that's 640,000. That's a lot bigger, than I was expecting. So we're going to get negative 40y plus 60y. So I'm just going to go ahead in the interest of board space and time. Negative 40y plus 60y is going to give me plus 20y equals 840,000. So subtract over the 640,000 in a stroke of plot convenience. That knocks us down to exactly 200,000. Divide by 20. And that ends up giving us 10,000 for Y. And if you take 10,000, plug it back in here, we'd get 6,000. So the final answer to the question is, how many tickets should we sell? Or how many tickets do we need to sell? We need 6,000 upper deck tickets to be sold, and then 10,000 lower deck tickets. So, again, keeping track of how the variables correspond to sort of the layman's terms, real world, if you will, examples in play. All right, so that's section 1.5, dealing with systems of equations. We're actually going to see later on in the course, we get even more involved with this, where we have more than just a pair of equations and a pair of variables. But for now, I think 2 and 2 is plenty. All right, so we're going to wrap up this chapter starting in our next video with some more, examples, some applications. That's actually like the section heading. So if for some reason you don't have enough applications yet, stay tuned.